systems that support that. We also have a second back room, which we call the SI room, which has our instrument team in it.
In fact, I think that person on screen that I see now is Bill Oakes. He has
Yes,
been.
that's Bill Oakes.
Yeah, exactly. That's right. So tell us a bit about Bill Oakes' role in this mission.
He's the program manager for JWST, and he's over the whole program, both the operation side, the development side. Everybody eventually works for Bill as you go up our chain. So he's been great, and he probably doesn't even know that he's currently on camera.
So one of the things that people were asking before is how are we actually getting this information down from the spacecraft? So you mentioned that there's telemetry. There are detectors all over the spacecraft measuring things like electrical current or temperature or all of these things. But how is that data actually getting to us here at the Space Telescope Science Institute?
Oh, that's an interesting point. So we have antennas on our observatory, and if people had watched along, one of our very early deployments was one of our antennas, and from that, signal is transmitted down to the deep space network. So this is the same network that we communicate with, let's say, the Mars rover on. There's one in Canberra, there's one in Madrid, there's one in Goldstone, and these very large dishes then take that signal, convert it into something that can be sent on a ground network, and it's sent by ground network to here, where we are both the Space Telescope Science Institute, and the once it comes into the institute, it goes through a whole series of processing, and then it comes up to our screens and monitors in a way that we can interpret.
Completed successfully. We're ready to continue with 693.027, bottom wind door sync. The command line looks good. You're good to execute.
Roger.
So
and you're good to
that was the last.
To continue. If you have the go.
That was the last set of commands sent to get the motors ready to verify that the motors are ready before we go ahead and do the launch lock release.
Yeah, it takes forever to get there.
And in the top view, we have our deputy program manager, John Durning. Not sure what his sign says. It says commissioning manager, but he's the deputy project manager. He works directly with Bill Oakes.
I believe we're about 2 minutes now away from firing. For those of you who may have just joined us, you're watching at live coverage of the unfolding of the primary mirror for the James Webb Space Telescope. Yesterday, they successfully unfolded one of the wings. I believe that was the port, the left side wing. And today we are doing the final wing, which will hopefully by the end of the day leave the primary mirror completely extended and unfolded. So we're only a few minutes away from that command to start, first slowly and then a little bit more quickly, unfolding that wing of the telescope. And you can see the configuration the telescope is in on the left side of your screen. This is a computer image, but it's based on actual real-time data from the observatory. So this is what Webb would look like if you were out there to see it. Of course, it would also look a lot darker because the sun shield now is completely blocking light from the sun and any sort of heat from the Earth and the Moon. And the telescope is operating very dark and very cold, as it was designed to do. So we're very close. I believe the calls will be coming shortly, so we'll probably take a pause in conversation now and begin listening to the calls. And Julie, as we have time in the conversation and the calls come, please step in to tell us what those commands mean and be our interpreter so that we know how this process is going.
Almost in the window, but not quite.
Sure.
Good God.
I have to say it's tremendously exciting for me. I have been looking forward to this quite literally for decades. This is something that has been a part of my family, have worked on this. And so this is a very proud and very exciting moment for me. It's been an incredible couple of weeks. Julie, how are you feeling? I know yesterday we ended up smiling a lot as we saw that wing move into place. Big smiles. I know that one of the things that was tremendously important to the
Copy.
unfolding of this telescope. Oh, let's just listen.
Here we go.
He's the only one left, right?
COC, I have confirmation from despliegue that they agreed that all of the sync moves look good. We're ready to command the launch lock releases. We're ready to go with 693.029. All channel safe verify. The command line looks good. Your go to execute.
Copy that. Did you have to go to execute?
Executing. Executing.
Your go to continue.
Copy, go to continue.
And at this point, they're going to send the command, which puts a current through a fuse wire and releases the launch locks that are holding the side of the mirrors back against the structure of the back plane of the mirror. And that was done so that we fit inside our fairing of our telescope. We were all folded up like origami. Obviously, the sun shield has been deployed, and you can see how big that is relative to the mirror itself right now. So the last of this is to bring out the mirrors, and then we will have our telescope mirror fully deployed.
And that's what makes this such a historic moment, is that this is the first time we've unfolded such a large space observatory. And first came the sun shield. Then there was the secondary mirror, the focusing mirror that had to come out in front of the telescope to focus the light. And then yesterday, the first of the primary mirror side segments, the wings, and then today the second one of that. This will not be the end today of commissioning the telescope. There's still more to come. One of the major things that needs to happen next is the focusing of the mirror. The mirror has 18 segments that all work independently and can all be adjusted independently. And we'll talk more about that after we unfold the wing segment. We'll have some time to talk with some guests to talk about that. But that's the incredible thing, is that this large observatory was folded up to fit inside the rocket, the Ariane 5 rocket, launched from Kourou, French Guiana, in South America. And now we are unfolding this observatory, and this is the first time this particular procedure has been done in space, and this is just wonderful to watch. So you were mentioning that you send a current through these. Is this an example of the actuators that we've been talking about before? That they're actuators that have to release, or this is something a little bit different?
No, this is the same. These are like a pin that's held in a like a cup cone assembly, and when the fuse wire breaks, it loosens up or wire that's tightly wound around it, allowing the pin and the cup to separate. All of that, all those little components are captured into the mechanism itself. So none of it's free floating in space as debris, but it allows those two pieces to move apart. And there's going to be 4 that actually fire today. They're just about ready to continue. I don't think we heard that on here. She says, go to execute.
Copy. Ceci, go ahead and execute.
Executing.
And your go to enable.
Copy, go to enable.
Copy, go.
And what they'll see now in their telemetry is they might see a disturbance on the entire observatory of these launch locks actually coming apart. The entire observatory might just as like when you unlock your vehicle, you can hear the click of the door unlock. There's almost like a little vibe in the whole structure that comes through that we can. Sometimes we can pick up in other telemetry.
And OCI confirm enabled. Your go to arm.
That these fully release.
Copy, go.
And in fact, I know the design of these actuators was specifically done so that they don't jar the telescope very much. They're actually very gentle.
Yes.
But even just that little bit of vibration can be
I see.
detected.
I confirm armed. We're waiting on the stored command sequence.
And the stored
Copy that.
command sequence is we don't ever want to break a command between the time we tell it to fire
Okay,
and
OC,
it
and
actually.
all stations, our next go will fire ordnance OTE, LRM Group 7. And OC, your go to fire.
Copy, go to fire. CC, you have to go to fire.
Certainly, everybody is a little bit, their nerves are, on edge, but lots of optimism, lots of excitement, and lots of smiles. So that's it's an emotional moment for all of us.
Everyone's been working on this since the day of launch. Our launch deployments started with our very first one that was caught by the rocket itself as it floated. JWST floated away from it, the upper stage, and it's been nonstop day after day since then. Having each deployment come along in series, everyone has gone very well.
OC, this is DepOps on Ops. I can confirm safe and disabled, and we're ready to continue with 693.031.
Copy that.
This is the step to actually do
Okay,
the
the
firing.
command line looks good. This is for OTE LRM Group 8, and you are good to execute.
Copy. CC, you have to go to execute.
Executing.
And you're good to continue.
Copy, go to continue. CC, you have to go.
There's a total of 4 mechanisms that do the launch lock. 2 are at the hinge where which is actually closest to us in the display, at the joints, 1 at the top, 1 at the bottom, and then 2 kind of hold the wing back to keep it from rattling during launch, and are at the far corners of
I
the
can confirm and
side mirrors.
you're good to arm.
Copy, go. CC, you have to go to arm.
I can confirm armed, waiting for the stored command sequence enable.
The thing that's so amazing to me is that what's happening today is the end of 178 release mechanisms. Every single one had to work.
Okay, all stations, our next go will fire OTE LRM Group 8. OC, you are go to fire.
Roger. CC, you have to go to fire.
Copy, go.
Yeah, there was a lot of work to put into these. A lot of people have heard about our single point failures. Each one of these itself was a single point failure. In other words, if one of those 4 launch releases does not release it, we're not able to move this side of the mirror forward into position. So this would be our last of these 4 single point failures. There's still other single point failures and some that stay with us for the life of the mission. Different areas of structure or a mechanism. If the mechanism fails, we don't have a second path of light to bring the light down. But these are major milestones in getting the observatory into its final configuration.
For those of you who are joining us, you're looking at live coverage of the commissioning of the James Webb Space Telescope. Today we are unfolding the second of the wings of the primary mirrors. Joining me is Julie Van Kampen. She is the Deputy Commissioning Engineer. You can see people there excited and happy.
Mom copies. Thanks, Step Lead. Glad to have the plot so we could follow along. Share your enthusiasm. That's awesome. 178 out of 178. Congratulations. Thanks.
They just fired.
It confirms that all of those
And they
mechanisms fired, 178 of them. Over
Yep,
the
and
course
I
of
could
the
hear
last
on the
I see this is
news.
step ops on ops. I see that proc has completed. We're ready to continue with 693.032 DEU to standby.
Copy that.
And they could see indications in
And the command
telemetry
line looks good. You're good to execute.
Copy to see you.
that
Have
everything
to go
was
to
successful.
execute.
Executing.
And you're good to continue.
Copy go. See you have the go to continue.
The next couple steps are going to be getting the deployment motors ready again. So before they checked them out, they had to put them into a standby mode while they were doing the firing. That was the safe configuration that you heard the deployment lead speak to. Now they're going to get them back into the configuration, and then they'll get ready to do their first small move.
AOC, I can confirm we're in standby round robin. We're ready for 693.033 to restore default torque limits. The command line looks good. Your go to execute.
Copy. To see you have the go to execute.
Executing.
And your go to continue.
Copy go to continue.
And earlier we had mentioned the position called MOM. That's the Mission Operations Manager. And the elbow we're seeing in the top screen, that's Carl Starr. He's the MOM of JWST. When they do the small mirror move, the small motor move on the mirror here, in our tool that we get to see on the screen, the OVT, the Observatory Visualization Tool, we don't actually, it's such a small move, we won't see the tool actually change at all. It won't be until the major move before we can actually see it on this tool. And it looks like they're calculating that's going to be another 20 or more minutes until we actually see the full move take place.
Right. We're sitting here now. We're actually watching the Mission Operation Manager, and you'll also be seeing live coverage from the MOC, the Mission Operations Center at the Space Telescope Science Institute in Baltimore, Maryland. I'm there as well, although in an isolated conference room, so I can speak to you unmasked. Of course, we're operating under COVID protocols, which has made a challenge, but it's a happy and festive day here, and we're really looking forward to this next deployment. Later on in the program, we'll have a chance to take some of your questions from social media, and today we're asking you to use the hashtag #UnfoldTheUniverse. So hashtag #UnfoldTheUniverse. We'll be stopping our commentary with your commands. So, we may have a conversation, but then we'll stop to hear how the commands are progressing. As first they make a very small movement to make sure the wing is moving correctly and all the motors are functioning correctly. And then in about 20 minutes from now, you will see on the left-hand side of your screen, you will actually see the wing click into place. And then after that, there will be a couple hours of latching it, of making sure that this is fully in its extended, permanent configuration. I see Julie's got a big smile on her face, which I love to see, because it's a lot of work.
So,
up at the top there,
again,
we're looking at Bill Oakes. Yeah.
Yeah.
Bill Oakes is the program manager, and you'll see him throughout this. As Julie said, he's sort of the head of the mission. Everybody kind of reports to him at this point. There's an interesting teamwork between scientists and engineers on a mission like this. And actually, Julie and I were talking about this earlier, that, I come from the background of being an astrophysicist. And when I think about Webb, I mainly think of all of the incredible data and the questions, the scientific questions that I'm looking forward to being able to explore with the telescope. Julie has a very different perspective. Julie, tell us a bit about your position as the deputy commissioning engineer. Tell us about what that job entails.
Sure. As the deputy commissioning engineer, I've worked to try to make sure all of the various pieces that it takes to commission the telescope come together in a way that makes an engineering sense. So there's a lot of people who have worked many, many years to make sure that it comes together operationally, working with how the commands are sent, how the control is done of the observatory, making sure our communications with DSN is worked out and timed with all of our activities. But I deal with the engineering aspect of that to make sure that if things are happening in a faster sense, that will still be safe. Like our operations can be handled 2 days earlier or 2 days later, should the timeline move one way or another from a hardware perspective. So many people are very interested in how the science will work, but I'm interested in how the parts of the telescope work themselves to make sure that they work together to actually give you that science.
Thank you. And that's the question, of course, about how you become an engineer or how you become a scientist. What is your background? I mean, what do you have a degree in, for example, that led you to this particular job?
My actual degree, both my undergraduate degree and I have a master's degree in mechanical engineering, and basically I started off being interested in how to design and build things. As a kid, I liked to build forts. You name it, I like to put it together. So I went to school to be a mechanical engineer, graduated from school. My first company was a small company, so you kind of got to do a little bit of everything. So you kind of learned to be the Jill of all trades. And from that, I moved to NASA and got into the testing department and was able to do actually a lot of the Hubble servicing missions from the testing side to get those instruments and components that were being sent to Hubble on the different servicing missions ready for those missions. Then eventually I moved over to JWST, and I've been on JWST since 2003. And I've been a systems engineer on the instruments and then the payload and now onto the commissioning.
Wonderful. So we will pause our commentary when we see your commands from the Mission Operations Center, but we do have time to take a few questions on social media. So whenever people ask questions like this, I'm touching wood right now. It says Nicholas on Twitter asks, would the observatory still be operational if one or a few of the mirrors break? Is there anything out there that could break them? So I mean, so that there's maybe a couple of different ways to answer this. I mean, what happens? All of the mirrors can be aimed independently. What happens if, for example, one of them doesn't aim correctly?
Well, the great thing about the Webb telescope is with these independent mirrors is that we can handle so many different scenarios like that. For instance, if one of the mirrors either, let's say, a piece of debris hits it, or during its launch and ascent phase, some of the stresses were higher than predicted, and we had a problem that broke a mirror or an actuator behind the mirror, we could actually take that mirror essentially out of the image by making it very much out of focus with the rest of the telescope. And if anyone's ever experienced having a floater in their eye or something like a scratch on your eye, you can realize how much you can see, and it is completely unaffected by that. So when something's not quite in sync with the rest of the primary mirror, there's different ways to take that impact out. Some of it's physically by moving the mirror out of its focus, and some of it's digitally by knowing that there's a imperfection that's going to be in each and every image that gets subtracted out digitally from those images.
Thank you. Maybe another social media question. For those of you that would like to actually have questions answered live on air with us, use the hashtag #UnfoldTheUniverse. So we'll be looking for hashtag #UnfoldTheUniverse to take your questions on social media. And so this actually kind of goes along with the second one. So Michael on Facebook asks, what protects the mirror from micrometeors and other fine space dust debris? I think the answer is not much.
Nothing. What you see is what you get. The sun shield is facing the Earth and the sun. So not only does it protect it a little bit from a little bit of possibly dust or anything coming from the sun, but the heat of the sun is basically what it does. If the sun shield itself, this isn't quite the question he asked, but if the sun shield itself got hit by a micrometeoroid and got a little tear or a rip in it, that's part of why we have 5 layers, and we can tolerate so much damage throughout time. And that was part of our lifetime calculations to make sure, based on our little bit of knowledge that we have of other observatories at the L2 point, to make sure that the environment there can be sustained by all of our optics and all of our sun shield over the time span that we expect to be there.
And just to give you an update, you're looking at live commissioning of the James Webb Space Telescope. From what I understand, there will be a call in about 4 minutes releasing the larger mechanism, and then about 4 minutes after that, we should be able to see the wing start to move. So in a bit under 10 minutes, we'll see the wing move.
Yeah, the first release.
At this time, we're ready to continue with 693.034 DEU to operate frame 6.
Copy
What
that.
they'll do is,
Command line looks
With
good.
the-
You are good to execute.
Copy. To see you have to go to execute.
Executing.
And you're good to continue.
Copy, go to continue. To see you have to go.
when they do the small move, this will verify for sure and for certain that all of those launch release mechanisms have released and that the mirror is free to move into its final position.
Right. Continuing our conversation, I mean, some small impacts from micrometeorites will happen. You know, over the lifetime of the mission, there will be some damage to the mirrors of the telescope. I remember at the Goddard Space Flight Center, when they replaced some of the cameras on the Hubble Space Telescope, they brought some of the old cameras back for analysis.
And DevOps can confirm operation frame 6. And we're ready to continue with the small motor move. So we're ready to go at 693.039.
Copy. It's on the window.
That command line looks good. You're go to execute.
Copy that. To see you have to go to execute.
Executing.
And you're go to continue.
Copy, go to continue. To see you have to go to continue.
Copy, go.
And stand by while we review parameters.
Copy that. Sending.
So we were talking about the debris. Also, being at L2 is very
See
useful.
the parameters look good. You're go to move the motor.
Copy that. To see you have to go to move.
Copy, go.
And pro complete.
DevOps copies, and you can queue up the stop.
Copy that.
And the motor status is moving.
Copy.
I was saying, got it. I remember the cameras being brought back for analysis. And they were analyzing every tiny little crater that was made by a little piece of dust or a little piece of debris. So, but you said that L2, for example, is actually a very nice place to be. It's actually a kind of a cleaner place when it comes to space junk. Is that correct?
Yes. Low Earth orbit, which Hubble is in, has a lot of space debris, as everybody has seen. I think it's gravity.
And OC, you are go to execute stop deploy.
Copy that. OC, you have the go to execute.
Execute.
And you're going to continue.
So
Copy go to continue. OC, you have the go.
Copy go.
they're stopping the motor move now.
And OC, the motor is stopped. At this time, we're ready to continue with 693.041 DEU to standby. Clock looks good. You are go to execute.
Roger. OC, you have the go to execute.
Executing.
And you're go to continue.
Copy go to continue. OC, you have the go.
Copy go.
Once they've taken a moment to analyze their telemetry and then move on again with the mirror moves, they're going to take the motor and they're going to drive the mirror up against a hard stop. Once they move it up against the hard stop and they verify that they're happy with that position, then they're going to start moving some latches into position. But when they move the latches into position, they'll kind of back off on that deployment motor a little bit to make sure that the latches are the ones that...
DepOps can confirm standby round robin. At this time, we're ready to continue with 693.042 to restore the gain stat parameter to default. That command line looks good. You are good to continue.
Roger that. OC, you have the go to continue.
Executing.
At
And
this
you're
point,
good
they're
to
just
continue.
Copy go. OC, you have the go.
Copy go.
sending some configuration commands to the motors.
So once again, you're joining us for the live commissioning of the James Webb Space Telescope. The starboard wing of the primary mirror is being deployed today. In just a few minutes, we should be able to actually see it moving. On the left-hand side of your screen is a real-time visualization based on telemetry, based on data from the telescope. It's generated by a computer. This is not a camera. We do not have cameras, unfortunately, on board Webb, but this will show us the configuration that it's actually in real time. And in just a few minutes from now, we will begin actually bringing that side part of the primary mirror around to form one large mirror of 18 segments. The segments that you see are colored gold. We'll talk more about the mirrors after we do this deployment. We'll have some time as the telescope is latched into its final configuration. But that is actual gold, very, very thin coating of gold, just a few hundred atoms thick. And the telescope would actually look quite a bit darker than you see it in that animation. The sun shield is blocking out all of the light from the sun and any reflected light from the Earth and the Moon. And so those mirrors right now are exposed to the dark, cold space that it will be doing its primary science, looking out into the universe. I understand the call to move is imminent any moment now. And when the mirror begins to move, we will just all sit back together and enjoy watching that. And we'll come back with commentary after that has completed. And we have some time as they latch telescope, a couple of hours into its final configuration. So we'll have different guests and experts to talk about what's going on when that happens. I'm joined by Julie Van Kampen, and she is the Deputy Observatory Commissioning Engineer.
RTCP is complete.
DepOps and DepOps copies. It looks like that load completed successfully. We're ready to continue with 693.043 DEU to operate frame 6.
Copy that. It's on the window.
And the command line looks good. You're go to execute.
Roger that. Lucy, go ahead and execute.
Executing.
So they've just put the
And you're
mirror
go to
back.
continue.
Right.
Copy, go to continue.
The deployment motor back into its operational state. It was taken out of operational state to do a reconfiguration. And now it's ready to do the full move once this is done.
We're coming to you live from the Space Telescope Science Institute in Baltimore, Maryland. This is happening in real time. The James Webb Space Telescope commissioning the final wing of the primary mirror. You're looking at live coverage from the Mission Operations Center, the MOC. And the command to deploy the wing is imminent. We're waiting for it any minute now, and then we will watch on the observatory visualization tool to see that. It'll just be a couple of minutes, something like 4 to 5 minutes. And then after that, we will come back with more commentary about the observatory, and we'll talk to some of the people that are some of the science leads as well about some of the scientific questions this observatory has been designed to answer.
They've just given the
Stand by
command
while we
to
review
go
the
ahead.
parameters.
Okay, standing by.
They're reviewing the parameters to move
Okay,
the
I
mirrors.
see those parameters look good. You are go to move the motor.
Copy, go to move. Lucy, you have to move. There you go.
Copy, go.
And this will move the mirrors into their final position.
Now complete.
The screen to the right shows us our ground station.
And the motor
Okay.
status is moving.
You can see the mirrors move in the visualization tool. It will take about 4 minutes for them to completely come forward.
And a reminder, this is real live footage. There's a 3-second time delay. It takes that long for light to travel at 186,000 miles per second. The James Webb Space Telescope is now well over 600,000 miles away.
And
The thing to
the-
remember about this,
Go ahead.
I was just going to say, just remember that this visualization is real. This is not pre-recorded. It's based on actual data coming to us from the telescope, being downloaded right now.
And the important thing about the light delay is not that the light takes that long, but the data, which moves at the speed of light, takes that long to come to us. I know that was a question we had on some of our
This is
social
Lead
media
on
before.
ops with the status. We have started our deployment into the deployed hard stops, and our current looks really good, nice and low.
Mount copies.
That was another of our deployment engineers confirming that everything looks good with our mission operations manager.
It's exciting to actually see it moving. You know, there it is on the visualization tool. It's getting closer and closer.
Yep, it's going to be momentous when it finally comes into position.
The first wing was successfully deployed yesterday, and now this is the final part, the primary mirror being put in place. Julie, give us a sense of the scale. These mirror segments. I mean, I had the honor of watching this being built. A lot of it at Goddard. How big across, for example, is one of those hexagons?
They're about 1.5 meters across from tip to tip. The hexagons are quite large. It's amazing to actually be in the clean room and look up to see the whole mirror assembled, towering above you. There's no amount of seeing it on photos that kind of gives you the sense of actually standing next to it in our clean room when it was assembled. And as we talked about before, and once it's fully into position here, the final shape that our primary mirror is going to be called a tricontagon. It's about a polygon.
The step lead on ops. We're about 3/4 of the way through the deployment, and everything still looks really good.
And the mirror itself will be concave. You can sort of just see that in this simulation. They actually have simulated some stars and things in space that you can see moving on the surface of the mirror. Also, as the mirror comes forward, and I'm not sure that we can see it at this angle, but there's a thing called the bat wing, and it's a shade that falls down behind the mirror to help shade any light or heat that might be coming up through the hole in the sunshade from keeping any of the backside of the telescope warm. There's one on each side that comes down passively as the motor moves this forward.
And
then the gaps between the mirrors are very small. I think it's on the order of several millimeters.
This is step lead on ops. We have reached the end of deployment, and we are preloading into the latch pads.
All right.
Okay, copy.
You see people clapping? Yes. Wonderful.
Everyone's up on their feet and clapping.
Wow, just look at that. The primary mirror is successfully deployed. This is a first. We have made a space observatory the mirror was so large that it had to be folded up to fit inside the rocket.
Okay, OC, at this time we're ready to continue with 693.046. Enable activate SCS 256.
Okay, copy.
And that command line looks good. You're go to execute.
Copy that. See, go ahead and execute.
Executing.
I think you can hear the relief in our deployment ops.
And you're go to enable activate.
Copy, go to enable.
Voice.
Copy, go.
I have to say, I just feel this kind of glow, in my chest right now, just seeing that mirror all deployed, all together. The size of a mirror allows us to collect more light from fainter objects, and in a lot of cases that means farther away objects that light took many billions of years to travel to us. A chance to see the universe as it was perhaps only a couple 100 million years after the start, after the Big Bang. The sensitivity of this mirror will allow that. And the size of the mirror also gives us a clearer, higher resolution, able to see more detail in space than ever before. So this was something that absolutely had to happen. We had to unfold this mirror. The secondary focusing mirror had to come out, and then a little bit more than a week ago, the amazing sun shield. And there it is in front of us. You're looking at this animation. This is not a pre-made animation. This is based on actual data coming from the telescope to us right now. We are live at the Space Telescope Science Institute, and we have successfully unfolded the last part of the primary mirror. After this, are still more commissioning acts to come, very important ones, for example, focusing.
Okay, DevOps can confirm that 256 is active in the delayed state. And I've confirmed with the depth lead, they're ready to begin the 3-door latch off stow and latch to safe. So we're ready to continue with 693.048, move 1 of 20.
Copy that. It's on the window.
And that proc looks good. You are go to execute.
Copy. This you have to go to execute.
Executing.
You just heard our deployment lead
Copy, go to continue.
go through a mouthful of description there of what happens next. There's a hook latch, and it's basically really that. It looks like a big latch, like you would hook possibly on a bathroom door or a tie down. If you had tie down straps to hold some packaging onto the back of a vehicle, it's actually a hook. And you heard her call it 3-door, and what that means is it's essentially it has a couple of different degrees of motion that it can do.
Stand by for perimeter review.
Copy that. Standing by.
Each of the latches are a little different in which degrees of freedom that they can move in, and so the 3-door
And
is
OC, the parameters look good. You're going to continue with the motor move.
Copy go. CC, you have the go to continue.
is one of the types that we have.
This latching procedure will take a couple of hours. We will be here through the entirety of it. We will be able to tell you when it is complete, and we may pause our commentary now and again, but we'll have different guests talking about aspects of the engineering and science of the James Webb Space Telescope through the next few hours. And this procedure will take quite a while. Can you tell us a little bit more about the latching, what we're going to be witnessing in the next few hours, Julie?
Sure. There's actually several latches. The next one that you'll hear her talk about will be one of the 2 doors, and there's 4 in total, I believe, and each of these will come into position, and then they'll very slowly. They want to make sure that they don't do something that's called like over-constrained. And as anyone who understands how a mechanism might move, you can easily kind of get yourself jammed into a position if you try to tighten one thing before you're completely aligned with another. Almost like when you change your tire, you want to kind of do that star pattern to wiggle it into just the right position to make sure it's flat. You don't want to tighten one of those bolts before you get the others snug, and you want to tighten them up in a pattern. So they'll do the same thing with these latches. They'll make sure that they're done in a very precise order, that the different degrees of freedoms of each of the latches are coming into play in the order that they had planned, to make sure that they get that mirror latched in and locked down in the absolute best position, so that those mirrors are in range for what they need to do for actually defining the surface of that mirror with the actuators and motions that will come next in the next couple weeks.
Well, Julie, thank you so much for being with us through this procedure. We're going to come back to you later on as this happens. At the moment, we are going to have one of our expert guests come up. We're going to be joined by
that motor move looks good. We are ready to continue with 693.049. 3-door latch to safe, move 2 of 20. And the command
Thank you
line
for
looks
having me.
good. You're good to execute.
Copy that. CC, go ahead and execute.
Executing.
Thank you for having me.
And you're good to continue.
Copy
And
go
we'll
to
come back to you
continue.
later.
CC, you have the go.
Absolutely.
Copy go.
The next person we're going to be talking to is the Associate Administrator for Science at NASA, Dr. Thomas Zurbuchen. Thomas, it is wonderful to see you. How are you feeling? Tell me about what you just observed.
Oh, I'm emotional about it. What an amazing milestone. We see that beautiful pattern up there in the sky now, almost complete. Of course, it needs to latch, but what an amazing milestone just ahead of it. 178 out of 178 of these actuators that had to fire the right way. I'm just so amazed and in awe about this team.
So one of the things that I'm just sort of, I haven't seen you for a while without a mask. They have us all in isolated rooms, and you're always clean shaven. You look a little bit different today. Is there is there some story behind that?
You notice, right? So, basically what happened is after we launched, frankly, I told my wife, I'm not going to shave until this entire telescope is fully deployed. This is like my favorite sports team. When they're in the playoffs, right? You have to be sure that you fully support them. So that's what I'm doing here. I can't wait to shave. Michelle, my wife, says, are they done soon?
And so I mean, that actually gives us a chance to talk a bit about what's coming out next. So, about how long do you think it's going to be until you shave?
Well, I fully expect, assuming that everything goes well today, I fully expect to shave today. And I just want you to know, this team is basically on track within a half a day or so of the fastest schedule that we had outlined. Frankly, I sat there today with some of the managers and said, if you ask somebody, 2 months ago, even
Okay,
a
the motor
month
move
ago,
is in
that, hey,
progress.
we're going
This
to be
one will
done
take
by the
about
8th of
14 minutes.
January. What would you have said? I said it's massively optimistic, frankly
Stand by for 14
unrealistic to
minutes.
assume that. I think this team is just incredible. Back to my sports analogy, we're seeing that the team on the playing field, and it's just an awesome team. And frankly, kind of over and above all expectations that anybody might have had.
You're talking about the team, and all coming together, but then there are also some tremendous challenges that this team has faced. And I know that that's something that you've been there with the team for quite a while now. Can you give us a sense about? I mean, not only did we have COVID, where we were all trying to do this and be isolated and be careful for each other's safety and all that, but there were all kinds of other challenges. I mean, tell us about some of the things that in your years on this mission, you were like, wow, I'm amazed they overcame that.
Look, I just want to tell you first, Michelle, I'm very humbled to be part of this team right now. And I know so many others were part of this team for decades before I even showed up. I've only been part of this team for 5 years, and I'm honored to be part of the team. Yes, we've had a number of challenges. If you, of course, look at everything that, go backwards, anything with the deployments, some of the challenges, frankly, that the team immediately addressed, they made it look easy, even though some of these challenges, frankly, were tough. You go back in time, and of course, it's very hard to think about the grit of this team that we're seeing without thinking of COVID, right? I mean, what's really amazing is how they overcame that, right? How they did not, they took every excuse they could to stay on track, right? It's so often, Michelle, we sometimes we see teams, in our private lives or even, elsewhere where all of a sudden, people take excuses to not fulfill goals. This team found every excuse to do so. You go back in time and you realize, how hard it is to be truly a single team. And Michelle, it's not just the engineers, it's the good people on Capitol Hill who are allocating the budgets, the people in the White House, all the stakeholders there. And I think what Greg Robinson, and for me, it's just really important to say that name, what he managed to do and kind of overcame is really building a team from the top all the way to the technician, the single team. And of course, that's why it's going so well, right? Because of, unified teams, are a beautiful thing to watch.
This is the depth lead on ops with the status. We're a couple minutes into our move to the safe position on the 3-door latch. Everything looks really good. Strains are low, and the strain offset came in right where we wanted it. So we're looking good.
Bomb copies. That's awesome, depth lead. Keep going.
So, as the associate administrator for science at NASA, you are a scientist, and there's some incredible scientific goals with this mission. And like we said, that this all started from questions. We launched the Hubble Space Telescope. We understood there was so many more things to see, even farther back in time. Give me a sense about some of the science that you're most looking forward to. Hopefully, that this mission will accomplish.
How much time do you have, Michelle? Right, I'm going to give you like a couple. But I've been doing a lot of reading and thinking about this kind of early universe and the galaxies, and for me, the potential impact of primordial black holes in this whole discussion, really the relationship of galaxies and black holes that are so tight. As we look at today's galaxies, kind of in our neighborhood, like how did that go there? For me, it just boggles my mind, to think of these enormous structures in the universe that are in the past. I'm going to give you a second example, Michelle, and of course, it's about finding life elsewhere, but I'm going to focus on our own solar system. We're going to make observations, for example, of Europa. We did that with Hubble. And there's amazing papers out there from in Nature and Science that says just marginally we can see kind of emissions of Europa that kind of are similar to Enceladus, for example, where water from these subsurface oceans is coming out together with organics at Enceladus. The question is, does that happen with Europa? And of course, we're moving towards a launch of Clipper in 24, and we want to make sure that if there are such emission points, that we know that, because we want to take the measurements with that amazing mass spectrometer on Clipper. There's similar type of discussions on Mars, where of course we're in the middle of another huge adventure trying to get these samples back in the first round trip to another planet. And for me, again, observations of the Martian atmosphere, its composition and its dust components are just so critical.
This is something that I think that, I've really enjoyed seeing your leadership on in the last years is no mission stands alone. We have missions, each one supports the other. It's not just this mission, then that one. There's a strategy that everything works together. So like you said, for exploring the solar system, you have something like the Webb telescope, which from a distance can see things like Mars, Europa, places like Titan. But then we have missions that are poised to go there and explore closer up as well.
Oh, I strongly believe that, right? What's so beautiful about nature and so amazing about the science program we have at NASA is the interconnectedness between the different questions that are there. And to me, that has always been one of the most exciting parts of studying nature, is to see relationships that were not innately recognized there. And I think the more we learn about nature, and especially in astrophysics, the more we see some of these connections, right? I'm always in awe. I read some papers, not as many as I would like to, Michelle, but nonetheless, I read some of the papers. I realize that atmospheric models of exoplanets so often are done by our good people in Earth science, because they know how to do it in ways that nobody else can. So yes, they belong together, all these missions, because nature is also interconnected.
Haven't changed significantly.
Absolutely.
Thank you.
Listening to commands from the mock, making sure we stay up to date on them. But absolutely. I mean, you mentioned the first stars. And there's probably plenty of people in the audience that don't really know your background as a scientist. Maybe you could give a little sense about your scientific expertise and how you came to be Associate Administrator of NASA.
Well, so I studied astrophysics, and I was really inspired by some of these missions. Frankly, I remember when I was 8 years old, I got this book about the Voyager missions and some of these telescopes that Nancy Grace Roman, right? It really started imagining. That was in the 70s when I got this book, and that inspired me out of the little mountain village in Switzerland to be where I am right now. I'm an astrophysicist, but I mostly focus my work about the sun and kind of the inner solar system. So I know how to do mass spectrometers, and I've worked with teams. And what I fell in love with, Michelle, is really the ability of working with amazing teams. When I see a team, whether it's in athletics, or whether I see it in this control room right there, a team that is truly operating at their highest capability, I'm so excited to see it. It's the most beautiful thing, but gives me so much hope of all these other things we can do. So when I look at astrophysics, of course, I think of the classes and so many of the things that I learned in the late 90s that are no longer true. And that's what science is about, because we learn all the time. Can you imagine, even in 5 years from now, how classes everywhere around the world will be affected by this very amazing observatory that's being set up right now?
Yeah, there's going to be some very, very profound things. I mean, you were talking about looking at some of the first galaxies to form. And this, of course, is one of the reasons why we have an infrared telescope, which is different from Hubble, which was largely in invisible light. Infrared actually allows us to see, to some extent, farther back in time, farther away in the universe, where the expansion of the universe has actually stretched out the light from visible light into the infrared wavelengths. And you mentioned this close relationship between black holes and galaxies. I mean, a lot of our viewers out there probably don't realize that we are orbiting around a giant black hole right now at about 500,000 miles an hour, the giant black hole in the middle of the center of the galaxy. And there seems to be some relationship between how galaxies form and how black holes form. But there's a real mystery about these big black holes that we see so far away and therefore so far back in time? Maybe give us a little more sense about this. Is one of the things that as an astrophysicist we look at and we say, I don't understand how that happened.
Right, it's truly a chicken and egg problem, right? Kind of right now, it seems to be the case that black holes and galaxies really coexist, right? It's actually really hard to find a galaxy in which there's no black hole there. It really seems that it's a really important part of the galactic evolution. But how does that start? Is the black hole first? What is the role of the black holes? From the beginning. You talked about the interconnectedness, Michelle. We're right now setting up a small telescope we launched a few weeks ago, IXPE, the Polarimetry Explorer, and hopefully next week we'll be able to give kind of first light of that kind of X-ray observation, kind of again providing new insights about some of these kind of more recent black holes, kind of really trying to understand what the mechanisms really are, and that in those black holes, but also the environment around it. For example, the roles of magnetic fields that are so critical in so many of these areas.
I know for me, one of the things is when you're looking at the universe. In the case of Hubble, we've been able to see black holes that are gigantic. They are millions of times the mass of the sun, and we're seeing them at a time when the universe was only, say, 500 million years old. And black holes, we tend to think of as being formed by stars that die. But when you think about the universe being that young, how did such a huge black hole form that quickly? And as an astrophysicist myself that studies stars, one of the things that I'm hoping Webb will shed some light on is the fact that the very first stars in the universe might have been quite different than the stars today. And maybe that's something you can give us a little bit of an idea. Why would the first stars be that much different from the stars we see around us right now?
I think it's a really great question, and I think it's one of the most amazing parts of really talking about how we relate to our universe. And that is that, of course, when the universe starts at the beginning, the atoms that form really are much less rich in terms of diversity than we have today. On my hands, I have gold and platinum rings that my wife gave me, and we know that those are not from the beginning of the universe. Frankly, they come from neutron stars that are merging, that are much, much later, kind of after a lifetime of a star. So when you look at the first stars, like what you have, kind of the material you build with is much lighter than stars that are kind of that most of the stars that we're looking at night through a telescope, because those stars are next generation stars in so many of the cases with much heavier components that are there. So the question really is, how do you build those first stars? And frankly, how do they then kick off that evolutionary process? There's a lot of models, and the data will, of course, constrain these models. That's what we call learning, right? It's say, this model is correct, this model is not correct. And by the way, there's an observation that none of the models predicts, which is the element of surprise. We can always bet on the element of surprise, Michelle. Frankly, often the surprising parts are the most important ones.
I sort of like that. We're talking about the history of chemical elements, but in there is always the element of surprise. Yes, the universe began, with hydrogen and helium, a tiny little bit of a couple other elements. But as you mentioned, everything that really makes us up, things that make up a human body, like carbon or the calcium in our teeth, or phosphorus or sulfur, the things that we need for our DNA.
We have completed this move of the 3-door latch to safe. So we're going to proceed with the 2-door latch.
One of the things that we're really hoping that the James Webb Observatory will shed some light on is what the universe was like before most of that formed. I mean, really the origins of the stuff that we are coming from. But there's another part of our origins too. You mentioned, in 5 years' time,
we're ready to begin the 2-door latch off stow. That is motor move 3 of 20. The command line looks good. You're go to execute.
Copy that. CC, go ahead and execute.
Executing.
And you're go to continue.
Copy go. CC, you have the go to continue.
One of the things that I'm really looking forward to is being able to maybe in a few years from now point to a star in the up in the sky and say that there's a planet around that star that has an environment similar to us here on Earth. Maybe to take us through how will Webb do that? How will Webb be able to explore what the actual environments on planets that far away around other stars? How will Webb be able to do that?
So if you go back in time of the Earth, of course, long before we were here, the atmosphere of our planet was very different. And frankly, the emergence of life on the atmosphere here, kind of in that Goldilocks zone, right, where water can cool, the emergence of life really changed the atmosphere. Frankly, there's a number of papers out there that said a large fraction of the nitrogen in our atmosphere may very well be from the emergence of life. There's other, of course, elements, oxygen type of, ozone, elements like that really come, of course, are very much part of that cycle of life that is here. So as we look at other planetary atmospheres, right, the question really is, what are the patterns there? And can we find patterns that are indicative of the presence, both the ability to have life there, but even in some cases, kind of the follow-up or kind of the consistency with life there. Certainly from what we've learned here, but perhaps also other versions that we yet have to we have to learn. Of course, what's so hard about life is we have n equals 1. We know only one life. All life on Earth is related, and we learned a lot when we went from one solar system to many solar systems, stellar systems. Frankly, many of the models crumbled within weeks of the first observations that were published in 1995. So when we look at life, I'm sure similar things will happen. But for me, that's why that's so exciting, Michelle.
Well, that's absolutely wonderful. So once again, we're speaking to Dr. Thomas Zurbuchen. He's the Associate Administrator for Science at NASA. Thomas and our audience out there, we're going to take a short break. We're going to take a pause in the commentary, and we will be coming back at 11 o'clock in the morning Eastern Standard Time to resume our commentary. But Thomas, thank you so much for joining us. What an exciting day, as you said, very emotional. And I'm just so pleased to be able to be here on the floor beneath you. So I'll wave to you from down in the building.
Yeah, I just really want to thank you for all the amazing work you've been doing, Michelle. It's just been wonderful. I've watched it many times.
And you're good to continue.
Copy go. Since you have the go to continue.
And stand by while we review the parameters.
Boxes, standing by.
See the parameters look good. You're good to continue with the move.
Copy go to continue. Since you have the go.
I see the motor move is in progress. This will take about 14 minutes.
Copy, 14 minutes. Well, stand by.
This is the depth lead on ops with the status. We are on step 4 of 20 of latching. We're latching the 2-door to the safe position into it a couple of minutes now. Again, strains look really good, nice and low, and our strain offset is matched our predicts, so no updates required there.
Excellent, Mom. Copies. Thank you.
This is Oceans.
is Dep Lead on Ops. We are halfway through this latching to the safe position on the 2-door, and everything still looks really good.
Welcome back to our live commentary.
Posty copies.
If you're joining us right now, you are looking at live coverage of the commissioning of the James Webb Space Telescope. I'm here at the Space Telescope Science Institute in Baltimore, Maryland. And what you're seeing on the screen above me is a live footage from the MOC, the Mission Operations Center for the James Webb Space Telescope. And then to my left is an observatory visualization tool, which is showing you real-time data, telemetry, as they say, from the James Webb Space Telescope, which is now over 600,000 miles away from us on its way out to an orbit about 1 million miles away, past the moon, L2, the Lagrange point. And just a few minutes ago, we successfully deployed the final part of the primary mirror, the side wing. So this has been a wonderful morning so far here in Baltimore. We still have a few hours to go as they latch this primary mirror segment in place.
successfully. We are going to continue at 693.054 to terminate SCS 256.
Copy that.
That command line looks good. You're going to execute.
Copy. CC, you have the go to execute.
Executing.
You're going to terminate.
Copy, go to terminate. You have the go.
Roger.
Copy, copy.
And OC, this is Step Ops. You are going to disable SCS ID 256, Step 55. The command line looks good. You're going to execute.
Copy that. CC, you have the go to execute.
Executing.
And you're going to disable.
Copy, go to disable.
Roger. RTCP is complete.
Copy.
Okay, and OC, you are going to execute the DEU stop deploy at 5-6. That command line looks good. You're going to execute.
Copy that. CC, you have the go to execute.
Executing.
And you're going to continue.
Copy, go to continue.
Roger. RTCP is complete.
Okay, OC DevOps can confirm that the motor is stopped. We're ready for 693.057 DEU to standby. And the command line looks good. You're going to execute.
Copy that. CC, you have the go to execute.
Executing.
You're going to continue.
Copy, go to continue.
Roger.
We're ready for step 693.058 to raise the integral gain.
Copy that. On the window.
And that proc looks good. You're going to execute.
Copy. CC, you have to go to execute.
Executing.
You're going to continue.
Copy, go to continue.
Roger.
Time we'll have some chance to recap some of the story of the James Webb Space Telescope, as well as talk to some of the expert scientists and engineers that are working on that. So if you're just joining us, you can also talk to us on social media. We ask that you use the hashtag #UnfoldTheUniverse. So hashtag #UnfoldTheUniverse, and we'll get to as many of those questions as possible. So this has really been a momentous day. Everybody is very happy with how things have proceeded. I think that it's a really nice chance to kind of go back and talk a bit about the larger story of how the James Webb Space Telescope got to where it is today, over 600,000 miles out in space and headed toward a Lagrange point, a balance between the sun and the Earth's gravity, where it will hopefully have many years ahead of it, observing the early universe, exoplanets, and all things like that. So this telescope has actually been in development for many, many years. A lot of people say that 1995 was the time when it began, when we started planning for this observatory. And what you're seeing now is some footage of actually putting together the primary mirror. Much of this work, building the primary mirror and the observatory and testing it, was done at Goddard Space Flight Center. These are acoustic and vibration tests, which were necessary to make sure the telescope could withstand the pressures of launch. So there's our acoustic test chamber, and you can see there the telescope is wrapped to keep it clean. This is a vacuum test that was done at Johnson Space Center in Houston. This is what we call Chamber A. This is the largest vacuum chamber that NASA has, and this was made during the Apollo era. It was actually large enough to fit full command modules of the Apollo mission in there to test. So what you're seeing now on the screen in front of you right now is live footage from the MOC, the Mission Operations Center. That's right above me as I'm speaking to you. And to the left is our observatory visualization tool. This is a computer-generated image, but this is a live image generated by data that's actually coming from the telescope as we speak. So what happened just a few minutes ago was the starboard side of the primary mirror, the mirror wing, was released into place. And that's an incredible accomplishment. The mirror is now fully unfolded, and that's for all of us here.
At this time, we're ready to continue with 693.059
It's an
DE to
incredible
operate
relief
from
and some
6.
incredible joy.
Command line looks good. You're good to execute.
Prior to that,
You'll see.
go ahead and execute.
Executing.
You'll hear me pause as I listen to what's happening in the control room. They are just making
good
sure
to
that all the
continue.
different launches are
Copy,
firing
continue.
successfully.
Roger, go.
And as I mentioned, this procedure will go on for a couple more hours. We will stay with it through the entire thing so that at the end we'll be able to tell you that the mirror has been safely latched into its final position. And that will mark the end of some major commissioning efforts of the James Webb Space Telescope. There is more to come. This is not the last phase. After this, we will be focusing the primary mirror, which is made of 18 independent segments. And then there will begin commissioning of the science instruments as well. So I think right now it's also a chance to sort of talk about the journey that Webb has been on. This is a portable, clean room. The Webb telescope, of course, had to be kept under very, very clean circumstances. And that left California on a special ship that is actually designed to take a lot of these specialized spacecraft cargo to the launch site that the European Space Agency runs in Kourou, French Guiana. This is in South America. And here you're seeing footage of that portable clean room with the Webb Observatory inside being taken off the ship and being loaded onto the place where it will go up on an Ariane 5 rocket. So that's part of the journey of Webb. And here you see actually opening up that portable clean room. Webb is in its stowed configuration, folded up. This is one of the reasons it's been so exciting the last couple of days. This observatory, for the first time, we've launched an observatory that was so big, the mirror had to be folded up. And as people often compared it to origami, folding up the telescope so it could fit inside the fairing of the Ariane 5 rocket.
Stand by.
And once again, moments ago,
parameters
we
look
saw
good.
the final part of that major commissioning of unfolding the mirror happen.
And OC, you are go to continue to move the motor.
OC copies. CC, how's it go?
As they continue the latching procedure, one of the things we can also look back on is the launch.
Queue up the stop.
This was a Christmas present for all of us. This was about 7:30 in the morning Eastern Standard Time in the United States. And there you see the launch of the Ariane 5 rocket. It was an absolutely perfect launch. They were able to get enough energy from the launch itself to save some of the fuel on the Webb telescope, which we hope will extend its life. And here you see some of the people at Mission Control in French Guiana cheering after the successful launch. And what you're looking at here is an animation of the observatory going away from the rocket. This is not an animation. This one here is the actual footage. There was a camera on the rocket itself. And here we see the Webb telescope coming off the Ariane 5 second stage on its way out to the Lagrange point, L2. That's about 1 million miles away from Earth. It's on the other side of the moon. It's a wonderful environment for an infrared telescope that needs to be very cold. Here you're actually seeing, again, this is real footage from the camera. You're seeing the solar panels unfold. This was the very first of the actual unfoldings that had to occur because now the telescope was able to power itself up using radiation from the sun. And then after that, of course, came the amazing. Oh, there's everybody celebrating. People, of course, put in huge amounts of time. They were here over the holidays. All of us have been working straight through Christmas and New Year's, of course. It's been wonderfully joyful, but there are a lot of families back at home that I'm sure missed us as well. Here's an animation of some of the major commissioning points that we've actually accomplished. So the solar array was unfurled, and also the antenna that allows the Webb to communicate with the Earth. Now you see the Webb moving up from the sun shield, which is now beginning to unfold. This is a 5-layer Kapton sun shield. It's a material that's very much like mylar. It's a very thin, very strong material. In this case, it actually has some silicon in it to make it more reflective, and also put together in small segments so that it's very strong and can withstand any sort of small impacts from micrometeorites, which we do expect over the course of the mission. And now that incredible sun shield is fully extended. The secondary mirror came out a few days ago. Yesterday, we saw the first of the wings of the primary mirror extended, and today we're just completing the second one. So now that we've gone through a little bit of an update as to what the tremendous journey that this observatory has been on, it's my pleasure to talk to Lee Feinberg, who is one of the senior engineers on the Webb telescope. And he's going to talk to us a bit more about some of these mirrors and some of the technology in Webb. So for one thing, Lee, wonderful to see you. We're all isolated from each other so that we can speak to you without masks. I'm downstairs.
He stopped at the spot he wanted to stop at.
Hi, Michelle.
And we are ready to continue to begin the 3-door cup latch to capture move.
So as we said,
and that is
the
move
reason I was
5 of
pausing
20.
Lee
The command line looks good. You are good to execute.
So in our conversation, you'll probably hear me pause just when I see that there's
Executing.
Lee, where you're sitting, can you hear those calls from
to continue. Roger.
I'm sorry, can you say that again, Michelle?
Where you're sitting, can you hear those calls from the mock?
I can hear them, yes.
Okay, right, excellent. So for one thing, but before we launch right into the technical, tell me a bit about how you're feeling right now. We're human beings first.
Yeah, well, I feel good. I feel like the mechanical and the deployment teams really have done a phenomenal job. The optical team actually is just about to get started, so it's sort of a transition time. But to see a full primary mirror, this is something we've really been thinking about for a long time, and it's just a great thing to see and to be ready to start aligning those mirrors.
Absolutely. Well, let's talk a bit about those mirrors. I mean, that's sort of the expertise that you bring with us. So to begin with, these are very different mirrors than most people are used to in their regular life, in many, many ways, obviously incredibly specialized. Tell us about some of the ways these mirrors are just completely unique and very different.
Yeah, well, let me start by just saying, when we started this a couple decades ago, we knew from the very beginning that one of the hardest parts of making the observatory was going to be the mirrors. And in fact, if you go all the way back to the first project manager, Bernie Siri, he used to have this chart that would show that, one of the key goals was to make a mirror that could be lighter than the Hubble mirror by about 10 times per unit area. And it had to work at incredibly cold temperatures, minus 400 degrees Fahrenheit. And it had to have a quality of the mirror that was approaching the quality of like visible mirrors, like the Hubble Space Telescope kind of image quality. And so these were, a set of challenges that were extremely difficult. There were some people who thought we couldn't even make mirrors that were this light and this quality. So actually it was a pretty collaborative effort. We actually worked with
other government agencies, including the Department of Defense. It was a collaboration to invest in multiple different mirror technologies. One of which was actually a technology in which the mirror has a bed of nails under it, a whole series of little tiny actuators. But one of them was a beryllium mirror. And the beryllium that was developed for Webb, it was actually a new form of beryllium. They called it an optical grade beryllium. And it was developed by a company that was called Brush-Wellman that then later became Materion. But this optical grade beryllium was supposed to be more uniform and was going to have better properties for being a telescope. And the key, though, was could you build large mirrors that are about almost 1.3, 1.4 meters in diameter? These are segments that are incredibly lightweight. So you have to be able to machine the mirrors from the back to lightweight them. And so it was a several-year technology development. It really took groups from all over the United States. The machining was done in Alabama, and the polishing was done in California. And here actually you could see some of the beryllium billets that were made in Ohio. So we developed the technology, and there was a mirror that was almost the full size of what the ultimate segments look like. We called it a prototype mirror. And here you could see the light weighting of the mirror from the back. And so that was the first phase, was just making a single mirror that could meet our requirements, including a gold coating that would reflect the infrared light. And so it was a large team effort. Ball Aerospace in Boulder, Colorado kind of led that team. And that mirror actually was competing with other mirrors. And we had a very intense process by which we selected which mirror technology we would use. But beryllium won out because of its superior qualities at these very cold temperatures. And that's really the key. Beryllium has this amazing property that when you take it to these very cold temperatures, it's incredibly stable. There's a material property called coefficient of thermal expansion. And for beryllium, that material property is like as perfect as could be at these very cold temperatures. And that really was one of the key reasons we selected beryllium, along with the fact, one of the big benefits is it's extremely light. And if you look at how large the telescope is, 6.5 meter diameter, if we didn't make mirrors this light, we would not be able to lift them with a rocket. So it was a long effort. We then had to manufacture the mirrors, but that's what led to the mirrors.
Has confirmed that the move 5 of
The story actually goes, even farther back than that. So where was the beryllium mined? You were saying that this is sort of a new type of beryllium, but where did it start? Where did the beryllium actually come out of the ground?
Well, so it's actually mined in Utah, it's mined in sort of these chunks and rocks that eventually will get ground up and eventually made into a powder form. And that was one of the things that they were able to do, was make a finer powder, a powder that has more spherical qualities. And then once you get that powder, and this was what Brush-Wellman did in Ohio, just outside of Cleveland. Once you get that powder, you can actually do a process that's called hipping. It's hot isostatic pressure. It's a process that puts heat and pressure on the beryllium and forms a billet of beryllium, a block of beryllium, that we would slice like an Oreo cookie into 2 mirror blanks. And that's how we got sort of the large blanks that would make up what we would ultimately then machine. And so the first step was to go from Utah to Ohio, and then they would be sent to the Cullman, Alabama, where the machine shop was, that would lightweight the mirror. And they would also put on the front surface, they would literally machine a surface that was approximately the surface we needed for each mirror. But that was only the beginning, because the next phase was you had to grind and polish the mirror. And that, typically when you make a mirror, it's the polishing that's the hardest part. And actually the hardest part of that process is testing the mirror. And one of the key things we had to figure out was, how do you test mirrors that are inside of a cryogenic chamber
and those parameters
to the level that we needed? And nobody had done that before. And we also needed to make sure that all 18 mirrors matched each other, so that if you made one mirror and then you made a second mirror, and you align them relative to each other, they need to have the same curvature. And that actually turned out to be one of the more difficult problems. So we had to develop methods, for testing mirrors and then for polishing the mirrors. When you cool a mirror down to minus 400 degrees Fahrenheit, it will literally deform because things shrink, but they shrink in a way that's not perfect. And so when we made these mirrors, what we did is we would put them inside of a chamber that would cool them down. we would test them with devices that are outside of the chamber. And once we knew how they deform, we would warm the mirror back up, send it back to the place that polished the mirror, and we would polish the inverse of the way they deformed. That process we call cryopolishing. And here you can actually see the mirrors going into the chamber. This is actually at the Marshall Space Flight Center. It's a chamber that was used for the Chandra Space Telescope, was converted for testing these mirrors. We put a special liquid helium shroud inside of it. And we also developed new test equipment that could work in the presence of all the vibration that we would get inside of a vacuum chamber. So we did all that work. We polished the mirrors with the inverse to deal with these cool down effects. And we also had to deal with the fact that these very lightweight mirrors deform under gravity. Right now is actually the first time these mirrors have ever been in microgravity, but on the ground there was always a gravity, and literally the mirrors are so light that the gravity would deform the mirror. So we not only had to polish them for the cool down, but we also had to polish them for the effects of gravity and deal with the effects of gravity. And so we had to combine all that with the fact that we had 18 mirrors that all had to match each other. So it was a challenging process. The whole effort from technology development to manufacturing was about a decade, from about 2000 to 2010.
It's absolutely incredible. And what you just said, the whole idea is you get these 18 mirrors, and they all have to work together as one single mirror. And that's a big part of the commissioning that's actually going to be happening in a couple in the future now. But let's talk about some of those. There's actuators on the back, right, that can control each of these mirror segments individually.
Yeah, it's funny because a lot of people see pictures of the Webb Space Telescope and they see the front, and it's gold and it looks amazing. But for an engineer, it's really the back of the mirror that is where all the engineering goes in. And in fact, maybe if we could freeze the picture in about a second, if you look at the back of the mirror, that's where all the engineering is. The first part was the light weighting and the rib structure and how you do that so that the mirror is strong enough to launch. But then you also have to be able to connect actuators to the mirror. And each primary mirror segment actually has 7 different actuators. There's 3 pairs of actuators that you can see in this video that we call them bipods, that literally allow the mirror to tip and tilt and move around in 6 different degrees of freedom. And then we have also one actuator at the center of the mirror, which allows us to change the curvature of the mirror. And so each of the primary mirror segments actually has 7 actuators. And it wasn't obvious exactly how to design those from the beginning. In fact, the very first design only had 3 actuators plus a central actuator, so 4 total. And as time went on, we understood better, how we needed to move the mirrors in order to make a perfect primary mirror over the full primary. And we also needed to understand how to mount those actuators. The actuators themselves are actually, an amazing achievement themselves. They were designed by Ball Aerospace using these special little gear motors that can move the mirrors in steps that are so small they're just a fraction of a human hair. In fact, the smallest step that we can move is about 1/20,000th of a human hair, and that is so that we can move the mirrors into position so that all 18 mirrors together will be aligned to less than a wavelength of light if you were to kind of go across the whole surface. And so we needed an actuator that could move in these tiny steps, but do it at minus 400 degrees Fahrenheit. And that's a lot of complexity and challenges. And then at the same time, these actuators have to survive launch, and so they have to be able to deal with, vibrations, large vibrations, and get the mirrors into the right position initially. Because when we launch the mirrors, we actually have them in a special position that is designed for launching them, where the mirrors are up against, we call it a hard stop, so they're in a nice, secure position. But actually, in the coming week, we're going to deploy the mirrors about a half-inch forward, each of the 18 mirrors, to this point where we can start aligning them. So these motors had to be able to get you forward by about a half an inch and then move in these very small steps. And so there's a lot of different challenges. It took a huge team of people across the country. There's companies that develop the motors in Florida, a company that developed the bearings in New Hampshire. I mean, all over, while Webb is an international collaboration, the telescope itself was actually built within the United States, but maybe 20 or 30 states made major contributions just to the primary mirror itself. That's how significant an effort it was, and that's how much coordination it took. The team from Northrop Grumman, the team from Ball Aerospace, the teams from L3 Harris and ATK that all worked on this primary mirror, they had to work with all these subcontractors from all over the United States to make all these pieces work together.
That motor moved.
In fact, I actually believe we have a map that we can show the different collaborators, all over the United States on the primary mirror. I think they're gonna run that. Yes, here we are.
Okay. Yeah. Yeah. I mean, it's literally all over the country, and obviously the people who kind of worked on this got a lot of frequent flyer mileage. But yeah, I mean, it was a team effort, and we had 3 different NASA centers early in the program working on this. I come from Goddard, which was the lead for the observatory and the telescope, and where it was all integrated. But we had the folks from Marshall Space Flight Center who had a lot of who helped us with the testing and the mirror technology. We had JPL involved in the algorithms, and then there was this large contractor team led by Northrop Grumman, but with companies all over the country. And for the mirrors, it really was Ball Aerospace that was the lead. So it really took a large collaborative effort. And one of the really neat things about it was when you work on something like the James Webb Space Telescope that is so incredible in its capabilities, it's not hard to get people to want to work on it. You get the most incredible people, and they're so dedicated because they know how exciting it is. And so, and they all, everyone worked really collaboratively. I know a lot of the folks who worked on this, from the people who were, ground the mirrors, the people who put the motors together. I know they're all following. A lot of them send us messages. A lot of them haven't even been on the program for over 10 years, but they're following every little step in detail with a lot of pride. And I will tell you that you see a few folks on television that you're watching in the Mission Operations Center, but for every one of those people, there's probably, hundreds of people who led up to that point who are all watching with pride. And that's what it took to get to this point.
Yeah, it's amazing. I mean, you talk about every step of the way. I remember at one point they were flying parts of the primary mirror for testing on the C-5, which is a gigantic aircraft that has this huge hollow interior that you can take very, very large objects. And I got a chance to talk to the flight crew, and these young men who were actually in charge of flying the airplane were so excited to be flying the James Webb Space Telescope. They just thought that was a wonderful thing to do. So we talked a bit about about building and testing the primary mirrors, and then the idea that these segments, like you said, they have to function in zero gravity, which is something that you can't do on Earth. You need to make sure you compensate for that, and also at the low temperature. But what comes next in commissioning is something pretty incredible, and that is getting all of these 18 segments to work together. And maybe you can step us through a little bit about what comes next, with a little bit of a timeline and what we're going to do to actually make this thing into one big mirror.
Yeah, well, so first of all, in just a few days, we're going to start exercising all the little motors. There's actually 132, we call them actuators, total on the telescope. There's 7 on each of the primary mirror segments, and there's 6 on the secondary mirror. And so the first thing we're going to do is what we call mirror deployment. That's about a 1.5 to 2 week operation. So that'll be starting actually as early as this Tuesday. And that's just to get the mirrors at a point where we can start tipping and tilting them in order to align them. But after that, we'll wait a little bit. We wait about a week or a little over a week for the instruments to get cold enough so that we can get images. So we can't actually we can't get first light until the instruments are cold enough. That's one of the things about being an infrared observatory. Is you need very cold detectors. So we got to wait for the instruments to get cold. But once that happens, the very first thing we're going to do is we'll look at a bright star, a bright isolated star, and we expect to see 18 separate images of that star that are really blurry. Okay, and it's not going to look real pretty. And
actually, we had an animation. I bet we could run that animation again.
Oh, okay, yeah, let's show that.
Yeah, that's right.
Yeah. So you can see light will come into the 18 mirrors. And they'll behave like 18 separate telescopes because they're not aligned yet. So each mirror actually forms a telescope between the primary mirror segment and the secondary mirror. And that makes a series of spots. And one of the first things we're going to do is find all 18 segments with those spots. And then ultimately what we need to do is get those spots on top of each other. So we'll align the spots, we'll align those primary mirror segments well enough that we have nice spots that we can form on top of each other. We call that the forming on top of each other image stacking. But it is a little bit of a long process because we have to take images, we have to figure out how to move the mirrors. We actually have a special wavefront room here at Space Telescope Science Institute. And we'll have a team of real experts from Ball Aerospace and from Space Telescope Science Institute and from Goddard that all will work together, and they'll get the images, they'll analyze them using software that they've rehearsed all of this with. They've done simulations of all this, and we've tested a lot of this with a testbed telescope that was built up. And they will go through and they'll get those 18 images on top of each other. And at that point, we're ready to get into what we call phasing. And phasing is a little bit like if you think of sort of oceans, if you think of waves in an ocean, imagine you have different surfers and they're each surfing on a different wave. What we need is for all of those surfers to be on the same wave. And so we need all of those mirrors to be essentially on the same wave of light. Light travels in electromagnetic waves, and we need them all to be on the same wave of light. Otherwise, we will get images that are kind of confusing. And so we'll go through a process. First, we go through a process called course phasing, where we'll get all the waves, all the mirrors lined up to maybe one or two waves. So imagine the surfers are almost all on the same wave, but not quite. And then we'll go through fine phasing. And fine phasing is the very final sequence. We actually use special algorithms that were developed primarily, actually, if you go all the way back to when Hubble Space Telescope had its blurry problem, the spherical aberration problem. There were algorithms that were developed to figure out the prescription of Hubble so that we could repair Hubble. And those same algorithms are actually being applied here to align the primary mirror in this very final stage. It's almost like you have a blurry primary mirror. And so we'll take images in the main science camera, the near infrared camera, but we'll take them through focus. We'll take different, it's almost like you move the focus on your camera. So we'll take a series of images and then we'll run them through these special algorithms that we've developed. We started with what we did on Hubble, and we've adapted them for the fact that this is a segmented telescope, but that's what's going to allow us to align this mirror perfectly. And eventually we're going to get an image of a single star. So a star will come in very early on, and maybe, a couple weeks, 3 weeks or so, it'll look like 18 separate images. But we think by sometime in March, we'll actually have a star form a single image. And that's kind of the first goal of the alignment process. And then from there, really what we're doing is we're aligning the secondary mirror to give us an image of a star that works in all the four instruments, over the full field. That takes about another month and a month and a half. So the whole process is about 3.5 months. We call it wavefront sensing and control. But really what it is it's aligning all these mirrors to act like a perfect telescope. And at the end of all that, we'll be able to hand off the telescope to the science instrument teams who will be finishing up their calibration and then get on with some of the early science.
Well, that's absolutely incredible, and that's probably a nice place for us to break, because we're going to bring on one of those scientists that is waiting to use Webb. So again, talking to Lee Feinberg, one of the senior engineers on the James Webb Space Telescope. Such a pleasure to have you here, Lee. Congratulations.
Thank you, Michelle.
And I hope the rest of the day goes very well for you.
Yep, thank you very much.
So for those of you that are joining us, you're watching live coverage of the commissioning of the James Webb Space Telescope. We are all here at the Space Telescope Science Institute in Baltimore, Maryland. And I'm Michelle Thaler. I'm from Goddard Space Flight Center. And if you'd like to join us later on, we'll probably have some time for social media questions. So you can use the hashtag #UnfoldTheUniverse. So once again, hashtag #UnfoldTheUniverse. And that will allow us to see your questions and answer some of them on air. So the next person that I'm going to talk to is Dr. Antonella Nota. And Antonella works here at the Space Telescope Science Institute. She's the representative for the European Space Agency. So Antonella, first off, many congratulations. It's been a wonderful morning so far. How are you doing?
It is amazing. It has been an amazing morning. And the team made it look so easy. We know how many years of preparation there were behind the moves this morning, but it just looked so amazingly easy. I'm so delighted to represent the European Space Agency at this time. And this is the moment we have been waiting for so long. So we are ready to move to the next step.
It's incredible. So for those of you that may have just joined us today, we deployed the second and final wing for the primary mirror. And that was a major commissioning exercise.
Yeah.
There are
Go
definitely
ahead and
things
take
to
direction
come,
from Dep
but
Ops. I'm
this
gonna
is,
go ahead
you
and
know, what's been
proceed
accomplished is
repeating
absolutely
step 060.
historic and really incredible.
Roger, Wilco.
You're looking at live coverage from the MOC,
CC,
Mission
I can
Operations
see
Center.
that command line, and that looks good.
And
You were
occasionally
good
you'll hear me
executing.
pause because we're listening to the
Executing.
commands. So that's all fine. And
you're
but
good at
in between
continue.
commands, we'll have a chance to talk to Antonella. So, Antonella, you are an astrophysicist, an astronomer, and tell us a bit about some of the major science goals that you're looking forward to. But maybe before we do that, we should back up a little bit and talk about infrared. Why is Webb an infrared telescope, and why is that so important?
It is infrared because it's the sources the Webb wants to look at emit in the air. For example, when we look at the distant universe, we're all familiar with the Hubble deep field that Hubble took several years ago. And we know those distant galaxies born 400 million years after
Standing by.
the Big Bang, just at the very beginning. Hubble, with the 2.4 meter, could push us to see that horizon. Webb will go way past and look at the first few million years and see those galaxies that are small, irregular, compact. We want to know how those galaxies became the Milky Way of today.
You are good.
And those galaxies emit in the infrared. Here you see a beautiful fly through the Hubble deep field, and it's amazing that in the size of a pencil we could see thousands and thousands of galaxies, including some very, very old, as I said, as old as 400 million years after the Big Bang. So we're talking 13.2 billion years old. And those galaxies look very different from today. And so I think the challenge for the astronomers is to understand how they evolved from how we look at them then and how we see them today. And Webb will do that. Webb will also be able to actually individually take spectra of these galaxies, because it has powerful spectrograph on board, including, for example, NIRSPEC, the workhorse spectrograph provided by the European Space Agency. And NIRSPEC will be able to actually take spectra. And for all of you who are watching, spectra are when the light of an astronomical target gets split into its component. Like, for example, rain droplets do after a thunderstorm, and you see a rainbow. So why spectra are important? Because spectra tell astronomers what the object is made of. Images tell us how objects look like, but we really want to know the physical, chemical composition, the elements that are there. And for that, we need spectra. And because Webb will be so powerful, 100 times more powerful than Webb, we do believe that we'll be able to take spectra of all these faint objects that we see at the edge of our observable universe.
We are ready to continue with the repeat.
It's absolutely incredible. For those of you that might not be familiar with the Hubble Deep Field, which was the image that we had started with there, when Antonella says the size of a pencil, it's looking down the narrow part of a pencil, that tiny little bit of the sky. Anywhere you look in the sky, there are many thousands of galaxies very, very far away from us. So again, and for our viewers, we often get a lot of questions about how is it that we're able to look back in time. A lot of people, I've actually gotten questions on social media recently about what direction do you need to look to see that far back in time. Maybe you could give us just a little bit of an astronomy lesson about how is it that we can view the early universe?
Yes, you look anywhere, because wherever you look, your eyesight basically looks as far as you can go. And the farthest you go, the farthest you go back in time. So as I was saying, these very faint galaxies that we see in the Hubble deep field have traveled the light for those galaxies has traveled for 13.2 billion years. So we see them today as they were 13 billion years ago. And this is the powerful of this amazing telescope. We can actually look at the beginning of the formation of the universe, because one of the things that Webb will do, it will be focusing on origins. What is the origin of our universe, as well as other origin things like how stars form, what's the origin of stars. So you can see the Webb is going to look, we hope, in the up to the first 100 or 200 million years after the Big Bang. If we're really lucky, we might even see the first star. Thomas was talking about first star earlier on. That's a challenge, but this is one maybe of the surprises that the web will bring us, together with many others, I'm sure.
I've also gotten questions about who gets to use Webb. I mean, how is it? One of the questions that I actually got on social media is, do only people from NASA get to use Webb? And that's very much not the case. You work at the Space Telescope Science Institute, where a lot of this happens. Give us a sense. How is time on Webb allocated?
Absolutely. So the entire worldwide community can use Webb to observe. They just need to have a good idea and a laptop and an internet connection, and they can submit their proposal. And their proposal, they will say, I want to use these instruments to make this amazing discovery, will be evaluated by a group of peers, experts in the various fields. And if that idea is compelling, that idea will be scheduled on the telescope. And as we speak, we have already a first year already scheduled of observations that have been given out to the community, to the instrument builders who have the right to get the fruit of their hard work over so many years, and the early release scientists who are actually...
And OC, Dep Lead's ready to begin with the 3-door latch to 200, move 9 of 20. And
yeah, there is a group of scientists
to execute.
Right or that, this you have to go to execute.
And you're going to continue.
Hope you go to continue.
This is so exciting to hear this and to hear, what's going on in the mock at the same time, which is one floor below. And kudos to the team for doing such an amazing work. For astronomers, this is the biggest gift that we can get. And we're just looking forward to see what will bring us. But I was saying the early release science, this is something that the director of STSCI used some of his precious directory discretionary hours to actually tell the community, submit proposals for approximately a couple of hundred hours. And they will be evaluated with this caveat. They will be done right away. The observation will become public. They will go in the archive. They will be made available to all, because this observation will show the capability of this very powerful observatory. So there are a number of programs, some of which Europeans, that are going to execute in the very, very first few months. And those are the ones that will show the world how actually Webb performs. Before that, we will have the early release observations. And those are really the ones that I'm waiting for to see. This is super secret list of targets. I don't know, what targets will be. But I know one thing, that they will be absolutely spectacular. And they will be shown to the world 200 days after launch, at the end of the instrument commissioning. But I hold your breath, because they will be just phenomenal.
I've been looking at the research.
So we've talked a bit about the early universe, and I know that another primary science goal of Webb has to do with exoplanets. And we mentioned that a little bit with Thomas, but I think maybe you could take us a bit more through how does Webb actually analyze the atmospheres of planets around other stars?
Absolutely. So this is a technique that Hubble had already pioneered. And I want just to tell the community who is listening, when Hubble was launched, we didn't know exoplanets. Now, we know that every star has exoplanet around. So this technique allows to study the atmosphere of the exoplanet as they move in front of their host stars. And by doing that, we can see via spectroscopy what actually the components of that atmosphere. And so you can see here the planet basically moving in front of the star, the light dipped, and in the infrared we can see important component elements that are the building block, we believe, of life in the future. So water vapor, carbon dioxide,
oxygen, all the complex molecules based on oxygen. Why we're looking for these molecules? Because the ultimate goal is to see if there is life out there. So we start looking at the building blocks. And Hubble has already moved the field forward, but it's a small telescope. We do believe that being 100 times more sensitive, Webb will just revolutionize this field. So our knowledge of exoplanet composition will be just spectacular. And maybe we will find another Earth out there. That's the big, award for this work.
Stand by for review.
Well, absolutely wonderful. Antonella, thank you so much for joining us. I hope the day continues to be joyful and exciting, and after this we all get a bit of a break. So thank you again for joining us. That's Dr. Antonella Nota, the European Space Agency representative here at the Space Telescope Science Institute. Thank you so much.
Thank you, Michelle. Good luck to all.
Thank you.
I see those parameters are good. You're going to continue with the motor move.
So the next person we're going to be talking to is Joe Spofera, and he will tell us a little bit more about some of the engineering aspects of the Webb telescope. For those of you that are just joining us, you're looking at live commissioning of the James Webb Space Telescope. I'm here at the Space Telescope Science Institute in Baltimore, Maryland. I'm Michelle Thaller. And Joe, thank you so much for joining us today. To begin with, please introduce yourself and tell us a bit about your role on the Webb telescope.
So you mentioned my name's Joe Spofera. So been working on the Webb telescope for 16 and a half years now with Northrop Grumman. Currently the program dynamics lead for Northrop, as well as doing a lot of lead responsibilities for deployments with the team that we have, both what we've done on the ground and what we're doing today here at the Mach for on orbit.
And how's the morning gone for you? Are you as excited as everybody else and happy that things have gone well?
Yeah, it's been going fantastic. It really has for the last 2 weeks as well. Kind of everything we could have hoped for with all of the operations have really gone quite nominal and quite to our expectations. So it's been a great commissioning so far.
So I guess one of the things that we have that we can show our audience are some footage from the tests that came before the launch of the James Webb Space Telescope, different tests in the clean room. So I believe we're going to roll some video, and you can tell me what we're seeing here, please, Joe?
Yeah, so this is actually the wing we're deploying today. So that was the ground deployment test for that wing the last time through. And actually, if we end up deploying both when deployed, this was our pre-observatory environment deployment. It was the last time that both wings were deployed at the same time on the ground. So you can kind of see the operations that went through there with all of the individuals in the high bay performing their jobs, getting through. So down on the left there, watching that wing deployment, that's Paul Reynolds, who's downstairs right now as the depth lead doing the deployment, kind of watching for what's going on, both like he would have on the floor there, doing observing the deployment, looking to see any interaction, seeing what's happening. And he's down there right now today with the rest of the Mach team doing that deployment, watching for the telemetry to make sure we see what we want to see during the operation.
And actually, in this footage, you can see that there's sort of this black border on the outside of the mirror, and that's for a very specific purpose. Maybe you could tell us a bit about that?
If you're speaking about the black border on the very outsides of all the mirrors, yes,
that's right. Yeah,
that's there for the frill section that goes around the outside, the fixed frill outside of the mirrors themselves for thermal purposes, so that you kind of have this deep black right next to the mirrors that would not pick up the reflections that the mirrors actually.
Roger.
And then, of course, that beautiful gold coating, and that's something that we get a lot of questions about as to why the mirrors are coated with gold. Give us an explanation for that, please.
I'm probably not the best person to give you the explanation for that one, but that is
the thing that amazes me is that all of this was done here on Earth. There was no way to take this up into space and test it in space. And of course, in space, you don't have the influence of gravity, whereas here on Earth you do. How do you design a test that you know that it's going to work in zero gravity? How do you design to take that into account when you're testing here on Earth?
Right, so the key thing there is we have to have a very good understanding of the loads that we want to see in the deployment and the loads that we want to kind of counteract or counterbalance in the gravity field. So we do want to try to maintain the resistances that we're trying to characterize or understand. So there are certain harnessing or insulation that provides a drag or resistance to the deployment. We still want to capture that in the test so we can characterize it and understand it on the ground. But you do need to counteract the gravity. You need to take away the fact that there's weight reacting on hinges and different locations in the deployable hardware. So there is an offload system that we use for that, and it was visible a little bit in the video that you did show, and I don't know if we'll be going back to that or not, but in the case of the wings, there was an overhead system, and actually you can see it right here. So there's a cable going up from the wing itself, from some hardware attached on the back so that we can attach basically through the CG of the wing. And you can see the cable running up to the crane structure to what looks sort of like a balance beam or a teeter-totter that's up there. And that cable, the beam that's up there can pivot and rotate, and the rotation point's aligned to the rotation axis of the wing so that you get a one-to-one rotation there. As the wing is turning, it's turning the hardware up above in the crane area. And at the opposite end of that rotating arm is also a weight to kind of balance that out. So you get a load or a tension in that cable that's effectively equivalent to what the wing weighs. So that now as you're rotating, the hinges that you have in this system don't actually see the weight of the wing. They're nearly weightless, as best as we can on the ground, so that you can instead try to capture just the loads of the nominal flight deployment, which would be, like I mentioned, something like a harness or some insulation, or some very low nominal drag that you get from driving at the one hinge as you rotate.
Absolutely wonderful. So it's been such a pleasure having you here, Joe. Congratulations again on everything that's happened this morning and the continued commissioning of the telescope that's coming up. So we'll let you go. Thank you so much for taking us through some of this testing.
Thank you very
good
much.
To have you here. So for those people in the audience that are just joining us, you're looking at live commissioning of the James Webb Space Telescope. Today we have successfully deployed the second wing of the primary mirror. We now have the whole primary mirror together, and we are currently involved in latching that into its final place. So that procedure will be happening for a couple more hours, and we'll be here to the end of it. Right now, however, we will probably take a short break in our commentary, and when we come back, we will talk to some more experts on the James Webb Space Telescope. You'll be seeing more live coverage from the MOC, the Mission Operations Center, here at the Space Telescope Science Institute in Baltimore, Maryland. And I'll be here to take more of your questions on social media. Once again, you can use the hashtag #UnfoldTheUniverse, and we'll get to some questions after the break. So thank you very much, and we'll see you soon.
I pulled up the YouTube stream at the TV Web.
Hello, Julie.
Hello.
So
we're currently in our final steps of the first latching of the 3 degree of freedom latch. This is the bringing it up to its full load. They've been, as you've been talking with your other guests, you can hear that they've been talking through all the steps as they move through all the different levels of load on the latches, and they're coming up on what they call the 3-door latch, and it's going to be loaded up to its final and complete step. As they've been going through, they've been checking out their system, checking out their motors, making sure that each step of the way that everything's good. They're in their final checkouts now, and this first complete latch is a big milestone.
Excellent. For those of you who've just joined us, that's Julie Van Kampen. She is the Deputy Commissioning Engineer for the James Webb Space Telescope, and I am Michelle Fowler. We're joining you from the Space Telescope Science Institute today in Baltimore, Maryland. And earlier in the day, we successfully deployed the final wing of the primary mirror. And what's going to be happening for the next couple of hours is latching that into place. Now, during our broadcast, you'll probably see us pause as we listen to commentary from the MOC, or the Mission Operations Center here. So if we're pausing mid-conversation, we will start right back up as soon as we get the call. And of course, we're operating under some very interesting circumstances today because of the COVID surge. We were all isolated. I'm downstairs in a conference room, so I can speak to you without a mask on, and Julie is in a room upstairs. So we're all isolated from each other to keep each other safe. You'll notice that everybody is masked inside the control room. We had a large and beautiful set at Goddard Space Flight Center that we were going to do perhaps a much more polished and professional looking broadcast. But in a way, this is kind of wonderful because it was so important for us to bring you all along on this very historic day. This is the largest and most complex space observatory ever built. It's built to answer some incredible questions about the origins of stars and galaxies and planets, the origins of us, the possibility of there being environments like the Earth on planets around other stars, and many, many things in between. So the rocket was launched carrying the James Webb Space Telescope on December 25th from French Guiana, from Kourou, that's in South America. It's now traveled more than 600,000 miles on its way out to its final resting place at L2. L2 is a Lagrange point, which is a balance point between the gravity of the Earth and the Sun. That's a wonderful, stable place to put an observatory. Webb is on its way out there right now. But as it does so, it is unfolding. The observatory is so large, it had to be folded up to fit inside the rocket. And that's a unique thing about Webb that has not been attempted before, this degree of unfolding and commissioning. And that's why we wanted to bring this to you live. Because this is a live broadcast based on an actual engineering event, the schedule is not known to the minute. The engineers will call out the commands, as they see fit and at the pace that they want to go at. So this is a broadcast that is not only live, but sort of, very much spur of the moment as we wait to see which commands come in and how long they decide to take from each step. But Julie, I think you can reiterate to everybody that things are going very well this morning so far, aren't they?
Yes. So far, our actual motion of the mirrors segments as they folded from being back alongside of the structure to its final position as you see it now in our visualization tool went extremely well. The motors worked perfectly. The launch releases before that went perfectly. And now they're in the process of latching into their final position so that those mirrors are aligned and ready for the next steps, which Lee had spoke to just a few minutes ago.
So I'm just looking at some of the social media questions that are coming in, and there's a lot of different ones on the mirrors. Actually, this is probably one that we can answer. So it's Jemison on Twitter states, my 8-year-old son wants to know why the mirror is a set of hexagons. Why was that shape chosen for the mirror? Julie, you can probably answer that one.
Sure. As you can kind of see in the picture, the hexagon shape packs in nicely into a circle. Most telescopes you can buy in the store or anywhere that you've seen typically in movies or whatnot is has a round mirror. It gives you the best amount of light collected per per use. It gives you a nice usable beam. The hexagon approximated that very closely. It has a nice packing shape. You can see how it fits in around the optics that kind of poke out. That nose in the middle is called the aft optics. It's the optics that kind of fold the beam a couple times before it sends it back into the science instruments. The outside shape of the mirror itself, it doesn't matter as much. Each of the edges of those mirrors are very carefully handled to make sure that they don't have glints off the edges, and to make sure that the edges are perfectly handled with how the gold coating reaches the edges of those. So the hexagon gave us a great shape for handling the mirror in its movement, the way that Lee had described, and it gave us the best approximation of round.
Okay.
And it's worth mentioning, we've got a couple different questions about the gold coating. So we're just going to pause, see what they're saying in the mock.
Go ahead. This is Ocean.
So at this time, I can really confirm that DepLead is ready to begin the 3-door cup latch to full, and that's going to be motor move 13 of 20.
Copy that.
And that command line looks good. You're good to execute.
Copy. CC, you have the go to execute.
Executing.
And you're good to continue.
Copy, go to continue.
Roger.
Nice to see you smile there, Julie.
Yes, so our first
when you think about the operating
position.
Oh, no, not at all. Let's say we're actually right now in the latching procedure. This will take a couple of hours as the mirror was moved this morning, and now it's being latched into its final place. There are a couple different questions on how we design things to operate at this very, very low temperature. In fact, I mean, this may be something that you as a mechanical engineer. So Jerry from Twitter asked, what kind of lubricants are required for the bearings of a wing segment and mirrors? Or are they electrically heated in the way that they can actually, move around at these very low temperatures? Like you said, I mean, not much more than, 100 degrees above absolute zero. Can you give us a sense about how you design an actuator to actually move and function? Things to actually swing around when they're that cold?
That's a great question. And it's been one of our major challenges. As you heard a little bit about Lee talking, and different times along our...
Copy that. Go to continue.
Roger.
That I'm sorry, I lost my train of thought. Thinking about what they were just saying about the latching. But when Lee was talking about the mirrors swinging into position, they have a particular type of lube on it. We did heat these particular ones up because they are what is called a wet lube, which means that we want them to be at a special temperature. Many of our other actuators, the ones that Lee was talking about, that on the backs of the mirrors and lots of other places throughout the telescope, call what is a dry lube. And most of the time the dry lube that's used is a molybdenum disulfide, and it's this it's essentially a very, very soft material that is not a liquid at all. It's actually a solid material that gets coated onto the surface of a joint, and the surface of the joint kind of smears across that soft metal and has a very low friction. It's interesting because we're using it at such low temperatures, and as we've talked about before, there was such a long period of time in designing and building Webb. So one of the major things that we had to go through was a lifetime test. And in our lifetime test, it's very difficult to simulate exactly how long you're going to be in test in the ground. So if you want to say that your mechanism is going to be good, from the day we coat our joint to the day that we're finished using it on orbit, and maybe that's a period of 10 years, maybe that's a period of 20 years, maybe we get, lots of fuel and we get to do it for 30 years. How do you get to qualify that?
Getting a lower transition to mass rate in an hour and 10 minutes.
So the operations on orbit, in a way, might be actually the simplest part of it. It's steady state. It's always steady state temperature. It's always a cryogenic temperature. It doesn't come back to air. It's never exposed to oxygen again. Oxygen is one of the things that can degrade surfaces. It oxidizes, creates little chunky pieces of oxidation. So once we're in orbit, we're pretty good with this. But the qualification had to figure out, well, how many times are we going to move this mechanism in air? How many times we're going to use it in vacuum? How many times we're going to use it at cryogenic temperatures? All through our testing lifetime. And then put on top of that, how long is it going to be used in space in those conditions? And will it have enough life of that joint? So that was a great question.
Yeah, absolutely. I mean, this is part of this idea of cryoengineering, making things that are going to work and work for a long time and work reliably under these sorts of temperatures. And actually, there are more questions coming in from social media about, like, for example, Dorian on Twitch said, how did you manage to test the focusing of the mirrors on Earth with all the deformations? So we've mentioned that it's not just, one of the deformations is caused by gravity versus no gravity, but there's also the deformations caused by temperature. And this is something that, I've had the pleasure of being able to watch for the last years, is all of the different stages of testing of this. Maybe you can talk a bit about some of the cryo tests of this that this telescope had to go through?
Sure. The way NASA approaches this, and all the contractors that work for us and ESA 2 and their nominal test program, is you start at the very most basic level. You saw some of the pictures of the mirrors being built and assembled, and Lee talked a little bit about their manufacture along the way. Well, that happens with every component. Is you start at the component level, like the piece parts, and you start at testing them and understanding them. And even at cryogenic temperatures, you might start off with just doing cryocycles to make sure that those...
Stand by.
Standing by.
So
hear us pause in the conversation as we listen to the bond. So yes.
Yeah. Sometimes I get more conversation about you.
Confirm that Dep Lead is happy with the 2-door latch to full. We're ready to continue with the 3-door. Oh, sorry. He was happy with the 3-door latch to full. We're ready to continue with the 2-door latch to full, and that is motor move 14 of 20.
Copy.
And that command line looks good. You are go to execute.
Copy that. CC, go ahead and execute.
Executing.
And you're go to continue.
Copy, go to continue.
Roger.
So just to wrap up our conversation on cryo testing, some materials, specifically our carbon tube material that you could see in our current visualization with the tubes that hang the secondary mirror out in front of us, are all of our backplane materials. They're made of a carbon structure that has a cyanate silosane polymer that binds all those carbons together, and that's a special polymer that's designed for high stability at cryogenic temperatures. But in order to deal with it at
parameter review
and know it at a cryo temperature, you have to go through cycles to kind of cryo stress relieve it. And the mirrors had the same thing. So there's lots of stuff that we do early on to help these materials deal with that cryogenic temperature.
So Julie, give us just a translation of the commands that are coming in now. What are they saying?
Go to continue.
Roger.
So they're in their final stages of moving each of these latches into their full position, so they get their full load on them, and this will be the final thing that holds that mirror down. We did this with the other side yesterday. Once it's in its final position, we never touch these latches again. Every motion from that point forward is happening at the mechanism level that's behind each of the mirrors and not at the frame and the structure behind it that we're latching into position today.
Well, Julie, thank you so much for joining us. Hopefully, I think we'll have a chance to talk to you a little bit later in the broadcast. For those of you that are just joining us, you're watching the live commissioning of the James Webb Space Telescope.
All stations, GSE on ops. Be advised, at this time we have just a little more than an hour before we begin our activities to hand over from DSN Canberra to DSN Madrid. That will start at 18:15 when we will lose coverage on the Madrid backup station, or Canberra backup station, DSS 36. We will have command and telemetry through Canberra Prime, DSS 34, for another 5 minutes. At 18:20, Canberra Prime will bring down their uplink, and we will have single antenna telemetry only at Canberra for another 5 minutes. At 18:25, Canberra will end their track. Madrid Prime, DSS 54, will start their track, then bring up the uplink as soon as they acquire telemetry. And at 18:30, 5 minutes later, our Madrid backup station, DSS 56, will acquire the downlink. So to reiterate, we will lose backup telem at 18:15, lose command at 18:20, get command back at 18:25, and get backup telem back at 18:30. There will be continuous telemetry despite the 5-minute command outage, except for a few interruptions. I will call them out before they occur.
Mom copies. Thank you, Jesse.
Once again, thank you for joining us, Julie. All right, so we're listening to live commands from the Mission Operations Center at the Space Telescope Science Institute in Baltimore, Maryland. I'm Michelle Thaler. For anybody just joining us, you're watching live commissioning of the James Webb Space Telescope.
Be advised, at this time you have 1 hour of command remaining on DSN Canberra.
Copy that.
What you hear them talking about is something called the Deep Space Network, the DSN. The way that Webb communicates with the Earth is that there are several large antennas, radio dishes around the world, and of course, as the Earth turns, different dishes come into view and out of view of the Webb telescope. The Webb telescope itself is now more than twice as far away as the Moon. It's about 600,000 miles away today, and it's going out to about 1 million miles away. A point called L2, the Lagrange point, a balance between the gravity of the Earth and the Sun. A wonderful place to park the telescope for the long and hopefully very successful mission ahead of it. It's been an absolutely incredible journey. The James Webb Space Telescope launched on December 25th from French Guiana, from Kourou. This is the main launch site of the European Space Agency, one of the major partners in the James Webb Space Telescope. Other major partners include the Canadian Space Agency and, of course, NASA. And the telescope has been on an incredible journey. I have been honored to be working at Goddard Space Flight Center while much of it was built, so I was able to see some of the testing and some of the building of the primary mirror, as well as the instrument package. And then it was shipped to Northrop Grumman in California, where it was actually put onto the actual spacecraft. And you see here some of the integration. You see that large primary mirror, and that's exactly what happened earlier today, is that the final wing was deployed. So we now have the full complete mirror deployed and is now being latched into place. What you see here is the testing of the incredible sun shield. This is a 5-layer shield made of Kapton, a very light, very strong material. Each one of those layers makes the layer above it a little bit colder until you finally get up to the telescope that has an operating temperature of under 400 degrees, under minus 400 degrees Fahrenheit. So just an incredible marvel. That was Julie Van Kampen, who was talking to us a bit about some of the testing that was required to make sure that different components actually worked at that incredible temperature. So here you see a beautiful picture of that large primary mirror. The mirror segments are each one of those mirror segments is a bit over 1 meter in length. So the mirror itself is about a little bit over 7 meters, about 7.5 meters across, which is absolutely incredible. A long journey to get it here from Goddard Space Flight Center, the different universities where instruments were built, to Northrop Grumman, where it was all put together and finally tested, and then put on a boat through the Panama Canal and to Kourou, and then the European Space Agency's launch site. picture-perfect launch early in the morning, Eastern Time, December 25th.
I'll see you standing by.
You'll hear me pausing in the commentary just so we can listen to what the commands are. Currently, they are latching the telescope into its final place, and it's been an amazing couple of days.
To continue with the motor move.
Copy, go to continue.
Roger.
The first thing that happened about a week ago was the deployment of the sun shield. That was very dramatic and incredible. And then came the secondary mirror. The secondary mirror is on a large boom that has to come out in front of the primary mirror. It's the focusing mirror. The light from all of those wonderful gold-coated mirror segments, they're all focused up to the secondary mirror, which then directs the light down into the instrument packages. And you can see here some of the major deployments that Webb has been through. The very first deployment, which we actually saw on cameras from the rocket, was the solar panels to power up the spacecraft. And here you see that incredible sun shield being unfolded. So there are the front and back components of the sun shield. Webb was then lifted away from the sun shield, where it will be isolated in cold operating temperatures, like I said, near minus 400 degrees Fahrenheit. And that was a baffle actually that was put up to help steady itself in the solar wind, a wind of particles from the sun. And now we're going to see the deployment of the sun shield. This, of course, is a computer animation. We did not have any cameras on Webb itself. But one of the things that we've been able to do today is see live visualizations from data from telemetry that's been coming down from the telescopes. So the telescope has been sending us signals as to what configuration it's in. And we've been following that this morning. And of course, that was one. Here you see that secondary mirror coming out on those long booms. And then yesterday, you'll see the next thing that happens is one of these mirror segments was clicked into place. That was the activity yesterday. And then this morning, the final wing of the primary mirror is in place. So we have a very special guest joining us next. We have Greg Robinson. And there are a few different people, including Thomas Zurbuchen, who had mentioned Greg earlier in the broadcast today as being one of the just most incredible leaders. This amazing team working together.
Depth lead has confirmed that the latch-off stow performed as expected. He's ready to continue to the top one door latch to safe, which is 16 of 20.
Okay, copy. Stand by one, please.
Standing by.
And Greg will continue with you as soon as we hear the end of that commentary from the model. I think we're good to go. Welcome, Greg.
Thank you, Michelle. Glad to be here.
Oh, what wonderful to have you here. Congratulations on this very successful and exciting morning. How are you feeling right now?
I'm feeling pretty good. This is certainly a huge milestone to complete all of the deployments. As you know, this was the stage where we thought we had the most risk in the mission. Still have a long ways to go, but certainly it's great to have this part behind us, at least in.
So tell us a bit about your role on the James Webb Space Telescope. I know now you are at NASA headquarters. And what has been your role for the larger mission?
So I've been on the program 4 years, so I'm the baby. My role as program director is to provide oversight to the project, execution, leadership going up to the administrator level, to what we call the non-floor, and external with our stakeholders, plus our international partners.
And people, time and time again, have commented on what a wonderful team this is. You know, can you give us some observations and maybe some personal stories about just how well this team has worked together under some very challenging circumstances?
Standing by. Stand by.
Standing by.
Yeah, this is certainly an amazing team. It's quite large.
We've reviewed those parameters and they look good. We are good to continue with the motor move.
Copy, go to continue.
Roger.
I'd love to hear the voices, but that means we're making great progress. So I'll stop in the time. Yeah, so a very large team across the globe. I think you've mentioned that. And certainly a lot of really good leaders at different locations at Goddard, at Northrop Institute here, and across the entire industrial base in the U.S. and across the globe. Really good team, certainly at headquarters at my level and Thomas, the administrator. We've had tremendous support, engagement, and focus. And so, and the two, it's kind of funny going into the mock class. I talked to many people, no idea which badges they wore, because it's truly one team.
Go ahead.
I think this is often something that surprises people about large missions, that it's not just a single.
This move will take about 14 minutes.
Just listening to the mock
Repeat
commands.
your last step-ups, please.
Oh, the move will take about 14 minutes.
14 minutes. Copy that. Thank you.
For those of you joining us, we're listening to live commentary from the MOC, the Mission Operations Center, and they are latching in place the wing of the primary mirror that was deployed earlier today. That process is going to take a few hours, and we will be here through the whole thing. So at the end of it, we'll be able to say that procedure has been completed successfully. But Greg, we were just talking about that. A lot of people don't realize that pretty much, all of the large missions that they may have heard of, and everything from Mars rovers to the Hubble Space Telescope and now the Webb telescope, these are international collaborations, and not just that, collaborations between industrial partners, government partners, university partners, all of that. Maybe you can give us a sense of just the range of partners that went into something like the Webb mission.
So the partnership, certainly internationally, includes the European Space Agency and the Canadian Space Agency. Truly great partners. They partner with us on many missions, and they've brought a lot to the table, instruments and the Ariane 5 launch vehicle. We really appreciate, of course, in the U.S. States, 14 countries across the globe. So a tremendous amount of support and engagement and actual development to get Webb to this point and further along in the operations. So it's been a huge team. And the industrial base is almost limitless. If I try to name all of the companies and institutes and universities, I'd probably be here until late today. And over the life of the development, more than 10,000 people have actually touched Webb. And externally, we talk a lot when we go to schools and things about technical careers. Many people have touched Webb, made it possible, including public affairs and finance, all types of disciplines. Of course, the heavy lifting was done technically.
And what was your path to Webb? You were mentioning all these different technical careers. So what was your education, and how did your career bring you to this point?
So I'm a double E, and I started my career in industry, and then many years ago, seems so long ago, at Goddard Space Flight Center. I've had many leadership roles at Goddard, at headquarters. I was deputy out at Glenn Research Center for a couple of years. And prior to this role, I was an SMD for programs, which consist of oversight of all of the SMMs. I think at the time there were between 110 and 114. And then 4 years ago, someone twisted both of my arms and said, let's go get this thing over the goal line. And I think we're pretty close.
Of course, you know that NASA loves acronyms. SMD stands for the Science Mission Directorate. And as Greg was saying, the Science Mission Directorate now has, it's over 100. Of course, it changes week to week as different missions launch and different missions come to the end of their lifetime. But over 100 missions, all being Science Mission Directorate at NASA. And again, perhaps for those of you who don't know what a double E is, Greg, what do you mean by that?
Electrical engineer.
Absolutely.
Sorry.
So this, the wonderful groundwork that you've laid with these partnerships, and working together, I mean, how would this mission shape the future of astrophysics at NASA?
So you've probably heard from some of us, you've heard from more. So from what I would call a layman standpoint, certainly for NASA, it's huge. It adds to the history of what NASA can do. Very complex, large missions that really open the doors for many discoveries. And of course, you've heard all of the discoveries we're certainly searching for with Webb, including looking back 13.5+ billion years between there. looking at habitability of exoplanets, and also studying within our solar system. So it's going to do a lot better than anything we have today. So certainly to that. But from a programmatic standpoint, it certainly shows within NASA, within the broader community, stakeholders, and across the globe, what NASA is capable of doing. And we can actually do a lot more when we have excellent partnerships like we have today with our two primary partners.
Well, Greg, thank you so much for joining us. Again, congratulations on a wonderful morning, but congratulations on the excellent leadership that you've lended to this program. And we're going to take a short break now. We're going to keep these images up in front of you. There you see Greg and me. And then when we take a break, you'll see continuous images from the MOC, the Mission Operations Center at the Space Telescope Science Institute, and also our observatory visualization tool, which you see on the left. This is a computer-generated image, but it's based on real-time data coming down from the observatory. So we're going to take a short break, and we'll be back in just a little while to continue our live commentary of the commissioning of the James Webb Space Telescope.